Hello friends and welcome to YouTube channel on Engineering Mathematics by Dr. Navneet. Friends, in this video lecture we are going to discuss about the applications of Laplace transformation for solving the linear differential equation. So in our previous video lecture already we had discussed about the Laplace transformation of derivative. So during that video lecture we had discussed such type of result. So first result is that if we denote Laplace transformation of y by y bar of s, so this is the notation to denote the Laplace transformation of y. Then if we take the inverse Laplace transformation, then we get this as y is equal to inverse Laplace transformation of y bar of s. Then second result was Laplace transformation of y dash. So y dash stand for the first derivative of y, or some people may write this as Laplace transformation of dy by dt. So to take the first derivative of y with respect to t, its Laplace transformation, then formula is s times y bar of s minus y of 0. Similarly, so this Laplace transformation of y double dash, that means second derivative of y, so we can write this as second derivative of y with respect to t is equal to s square y bar of s minus s into y of 0 minus y dash of 0. Similarly, for the third derivative of y with respect to t, formula is s cube y bar of s minus s square y of 0 minus s y dash of 0 minus y double dash of 0. So we can continue this result up to nth derivative. So as per our engineering curriculum, so we required the results up to third derivative of y with respect to t and its Laplace transformation. So already we have learned this concept during our previous video lecture. So this is just a revision of that lecture. Now friends, in today's lecture we are learning the applications of Laplace transformation to linear differential equation. So this LDE stand for linear differential equation. So now for solving example based on linear differential equation, there are 5 important steps. So let's try to understand the method of solving linear differential equation by Laplace transformation concept. So first thing is that, so whatever linear differential equation is there, so for that linear equation apply the Laplace transformation to both sides. That means apply Laplace transformation to right side as well as left side. And second step is that, so after applying Laplace transformation to left and right side, so use this result and write down next step. Then after that, second step is use the initial condition. So in this result, so there are term y of 0, then y dash of 0. So for this y of 0 and y dash of 0, so initial conditions are given. So according to the initial condition, it may possible that we are having the value of the type y of 0 is 0, then y dash of 0 is 1. So this is called as initial condition. So put this initial condition in such type of equation. That is our second step. Now third step is that after putting initial condition, so whatever equations we are getting, so rearrange that equation in such a way that find the value of y dash of s. Then after finding y dash of s, so apply partial fraction. So after getting y dash of s, we are applying the concept of partial fraction because we are converting given equation in terms of standard form, so that we can easily apply the concept of inverse Laplace transformation. So here it is always possible for us to apply convolution theorem or standard result also, but in this video lecture we are discussing the partial fraction concept for finding the value of y bar of s, so that after applying partial fraction we get the standard equation for inverse Laplace transformation. Then finally apply the concept of inverse Laplace transformation. So these are the 5 important steps for solving example based on the linear differential equation by Laplace transformation. So friends, take the first example. So take the simple example using Laplace transformation solve, so take the first example using Laplace transformation, solve. Suppose first linear differential equation is dy by dt plus, suppose this is 2y is equal to e raised to minus 3t. So now here we can take the initial condition as y of 0 is 1. So this is the initial condition. So now this is the linear equation. We know the concept of linear equation. So now to solve this linear equation with the help of Laplace transformation, so now here first step is that apply Laplace transformation to both sides. So by Laplace transformation, if we apply the Laplace transformation to both sides, then we get this as Laplace transformation of dy by dt plus 2y is equal to Laplace transformation of e raised to minus 3t. So we apply the Laplace transformation to the both side, but according to the linear property, so these are the two terms, so we can split this into the two parts according to the linearity property. So we can write this as Laplace transformation of dy by dt plus 2 is constant into Laplace transformation of y is equal to Laplace transformation of e raised to minus 3t. Now friends, it is always possible for us to find out the Laplace transformation of this term and this term. So we know that this is Laplace transformation of dy by dt. That means first derivative of y with respect to t. So this result is same as that of the Laplace transformation of y dash. So according to this Laplace transformation of derivative result, we can write this as s into y bar of s minus y of 0. So this is the first value of Laplace transformation of dy by dt, then plus 2 times. So find the value of Laplace transformation of y. So we know that Laplace transformation of y is y bar of s. So we can write this as y bar of s is equal to. Now this is the standard result for finding the Laplace transformation. So according to the standard result for Laplace transformation, we get the value of this term as 1 upon s plus 3. So after applying Laplace transformation, we get this as the first step. So apply Laplace transformation on both sides. Now second step is that use the initial condition. So friends, here initial condition is given, which is y of 0 is equal to 1. So in this equation, put y of 0 value as 1. So we get this equation as s into y bar of s minus this is 1, then this is plus 2, then y bar of s is equal to 1 upon s plus 3. So this is the second step for solving linear differential equation by Laplace transformation. Use initial condition. Now third thing is that find the value of y bar of s. So after rearranging the equation. So now if we take y bar of s common, then coefficient of y bar of s are, this is s and this is 2. We can write this as s plus 2 into y bar of s is equal to 1 upon s plus 3 plus 1. So after taking this minus 1 to the right side, we get this as plus 1. So in this way, we get this equation. So rearrange this equation and try to find the value of y bar of s. So if we simplify this right hand side, then we get denominator as s plus 3 as it is. Then this is 1 plus s plus 3. We get this as s plus 4 upon s plus 3. So first simplify the right hand side of this equation, then find the value of y bar of s. So value of y bar of s is, so this is s plus 4 as it is. So then after taking this s plus to the right side, we get this as s plus 2 and this is s plus 3. So in this way we get the equation. So that is our step number 3. Find the value of y bar of s. Now next step is that for finding the inverse Laplace transformation of this function, so we are applying the concept of partial fraction, because if we apply the inverse Laplace transformation to this equation for finding the solution of this equation, that means for finding the value of y, so it is not possible for us to get the inverse Laplace transformation of this function because this function is not in our standard form. Whenever such type of situation appear, apply the concept of partial fraction. So use of this partial fraction is that after applying partial fraction, we are getting equation in terms of standard form. So now observe that, so these factors are linear because power of s is 1 and these are non-repeated. We can write these as a upon s plus 2 plus this is b upon s plus 3. So now we can write its partial fraction as s plus 4 is equal to a into s plus 3 plus b into s plus 2. So after taking this denominator term to the right side, so s plus 2 will get cancelled here and s plus 3 will get cancelled here. So now this is the equation. So for our simplicity, let's call this as equation number 1. So now find the value of constant a and b. We know that this is very simple. So if we put s is equal to minus 2. So first put s is equal to minus 2 so that we get the value of a. So we get this as 2 is equal to, so this is a. So we directly get the value of a as 2 from the, after putting s is equal to minus 2. Similarly, if we put s is equal to, so for getting the value of b, so this must be 0. So put s is equal to minus 3. So we get this as 1 is equal to, so we get this value as minus 3. So that means this is minus b. So this implies that value of b is minus 1. So now put the value of a and b in equation number 1. So after putting the value of a and b in equation 1, we get this equation as, so I will write here. So here a is equal to 2 and b is equal to minus 1. So now put this value in this equation number 1. So after putting this value in this equation, we get this equation as, so we may write here, so we get this equation as, so 2 upon s plus 2, then this is plus minus 1 upon s plus 3. So in this way we get the value of partial fraction. So this is our step number 4. Now friends, apply step number 5. So apply the concept of inverse Laplace transformation. ILD stand for the inverse Laplace transformation. So if we apply the inverse Laplace transformation, applying inverse Laplace transformation again on both sides of this equation, then we get this as inverse Laplace transformation of y bar of s is equal to, this is inverse Laplace transformation of, so 2 upon s plus 2 plus minus 1 upon s plus 3. So we can easily write this step as, so which is equal to 2 times inverse Laplace transformation of 1 upon s plus 2, then minus, so this is inverse Laplace transformation of 1 upon s plus 3. So now friends, directly we get this value as, so inverse Laplace transformation of y bar of s. So according to this formula, so inverse Laplace transformation of y bar of s is equal to y. So we can write the value of left hand side term as y, which is equal to, so this 2 is as it is, then this is the standard formula for e raised to minus 2t, inverse Laplace transformation of 1 upon s minus a is e raised to minus at, so where a is equal to 2, then again this is minus, same formula is applicable, so we can write this as e raised to minus 3t. So in this way we get the solution of linear differential equation with the help of Laplace transformation. So these 5 steps are very important to solve any linear differential equation by Laplace transformation. So this is one of the simple example. So this is the first. Now let's take the second example. Now friends, let's take the second example. So second example is solve the linear differential equation by Laplace transformation. dy by dt plus y is equal to cos of 2t, where initial condition is y of 0 is 1. So now solve this example with the help of Laplace transformation. So now first step is take the Laplace transformation on both sides. So if we apply the Laplace transformation on both sides, then we get this as Laplace transformation of dy by dt plus this is Laplace transformation of y is equal to Laplace transformation of cos of 2t. So directly we apply the concept of Laplace transformation and linearity property for the Laplace transformation. So now we know that, so this is Laplace transformation of first derivative of y with respect to t. So this formula is applicable. So we can write this as s into y bar of s minus y of 0. So this is the first term plus Laplace transformation of y. Laplace transformation of y is y bar of s. So we can write this as y bar of s is equal to. So Laplace transformation of cos of at. So standard formula is s upon s square plus a square, which is 2 square. So 2 square is 4. So this is the first step where we apply the concept of Laplace transformation. Now second step is that use the initial condition and simplify. So friends, here initial condition is given, which is y of 0 is 1. So put y of 0 is equal to 1 here. So we get this as s into y bar of s minus 1 plus y bar of s is equal to s upon this is s square plus 4. So now after putting this condition, so third step is that find the value of y bar of s. So now to find the value of y bar s, collect all the coefficient of y bar of s together. So first coefficient is s. So this is 1. So we can write this as s plus 1 into y bar of s is equal to this is s upon s square plus 4. Then after taking this minus 1 to the right side, we get this as plus 1. So now just simplify this. So we get this as s square plus 4 as it is. This is s plus. So if we multiply these two this side, then we get this as s square plus 4. If we rearrange this numerator according to the decreasing power of s, then we get next step as s square plus s plus 4 divided by s square plus 4. So friends, this is the value of s plus 1 into y bar of s, but we required the value of y bar s. So we can rewrite this as y bar of s is equal to this is s square plus s plus 4 divided by, so this is s plus 1 and this is s square plus 4. So now in this way we get step number 3, which is very simple. Just rearrange the equation and find the value of y bar of s. Now next step is to apply the partial fraction concept. We are applying the partial fraction concept here because we are going to convert this equation in terms of standard form for applying the inverse Laplace transformation, because it is not possible for us to find the inverse Laplace transformation of this function directly. So first convert it into the standard form. So we know that, so these factors are linear. First factor is linear, so a upon s plus 1. So second factor is quadratic. We can write this as bs plus c divided by s square plus 4. So because second factor is quadratic factor. So now apply the partial fraction concept. So we get this as s square plus s plus 4 is equal to a into s square plus 4. Then similarly we can write this as bs plus c into this is s plus 1. So now our aim is to find out the value of constant a, b and c. So now to find out the value of constant a, put s is equal to minus 1. If we put s is equal to minus 1, then this factor becomes 0. So this whole term becomes 0. We can get the value of a. So if we put s is equal to minus 1, so then we get this as minus 1 square is 1. Then this is minus 1 plus 4 is equal to, this is 1 square is 1, 5 a. So we can directly get the value of a as a is equal to, so this is 4 upon 5. So this is the first constant we are getting. So a is equal to 4 upon 5. So we write here separately a is equal to 4 upon 5. Now next is to find out the value of b and c. So it is not possible for us to put the value of s in such a way that, so this first coefficient become 0, because here s square term is present. So this term cannot become minus or negative. So that's why it is not possible for us to find out the value of b and c by substitution. Now just simplify the left and right side. We get this as s square plus s plus 4 is equal to. So now arrange this in terms of decreasing power of s. We get this as s square, or for your simplicity we will first simplify this. So this is a square plus 4a plus this is bs square plus bs plus cs plus c. Now arrange according to the decreasing power of s square. We get this as a plus b, then s, collect all the coefficient of s. So coefficients of s are, so we get this as b plus c, plus collect all constants together. So constants are 4a plus c, 4a plus c. So now here this side is s square plus s plus 4. So if we compare the coefficient of s square, s and so on, so we get this as 1 is equal to a plus b. So because coefficient of s square is 1 here and this is a plus b. Now coefficient of s is again 1, which is equal to b plus c. So this is b plus c, and again we get this as 4 is equal to 4a plus c. Now friends, we already know the value of a, which is 4 by 5. So we can get the value of b as, so 1 is equal to a plus b. So b is equal to 1 minus a, which is 1 minus 4 by 5. So we can write this as 5. So 1 upon 5. So in this way we get the second coefficient, which is 1 upon 5. So I will write here value. So b is equal to 1 upon 5. Now similarly find out the value of c. So now from this equation we get this as 1 is equal to b plus c. So now we know the value of b, which is c is equal to 1 minus b, which is equal to 1 minus 1 upon 5. So we get this as 5 minus 1, that means 4 by 5. So this is the third value, which is c. So we will write the value of c as 4 by 5. So friends, in this way we get the value of constant a, b, c, and now let's put this value in equation 1. So for our simplicity, let's call this as equation number 1. Put the value of a, b and c in this equation number 1 so that we get equation in our standard form. So put the value of ABC. So purpose for this partial fraction is to get the equation in terms of standard form, so that we can easily apply the concept of inverse Laplace transformation. So y bar of s is equal to a. So value of a is 4 by 5 divided by s plus 1, plus value of b is, this is 1 upon 5s plus c, which is 4 by 5 upon, this is s square plus 4. So here this denominator is in our standard form, this is also in our standard form, so that we can easily get the value of inverse Laplace transformation. So now this is our step number 4. Friends, apply inverse Laplace transformation to both sides so that we will reach to the final answer. So if we apply the inverse Laplace transformation, then we get this as inverse Laplace transformation of y bar of s is equal to. Now just directly apply this concept. So this is, if we take 4 upon 5 constant common, we can write this as 4 upon 5 into inverse Laplace transformation of 1 upon s plus 1 plus, friends, this denominator is common. So this is first term and this is second term. We can split this into the two parts. So we directly write this as 1 upon 5 into inverse Laplace transformation of s upon s square plus 4. So for the first term, plus second term is plus 4 upon 5 into inverse Laplace transformation of, so after taking 4 upon 5 common, we get this as 1 upon. So this is 1 upon s square plus 4. So this is s square plus 4. So this is very simple. So we write this according to the linearity property for the inverse Laplace transformation. So now friends, apply the concept of inverse Laplace transformation. We know that this inverse Laplace transformation of y bar of s, inverse Laplace transformation of y bar of s is equal to y. So we can write the value of left hand side term as y, which is equal to 4 upon 5. Then this is the standard result for e raised to minus t. Then this is plus 1 upon 5 as it is. Again, this is the standard result for cos of 2t. Then plus again 4 upon 5 is constant. Again, this is the standard result for sine term. So we can write this as sine of 2t into 1 upon 2. So in this way we get the final answer to this term. So this 2 and this will get cancelled. So 2 2s are 4. So friends, this is the final answer to this question. So this is very simple technique. So for solving the linear differential equation by Laplace transformation. So now this is the second example. Now let's take the third example. So third example. Now friends, let's take the third example. So example is using Laplace transformation, solve the linear differential equation y double dash plus y is equal to t, where initial condition is y of 0 is 1 and y double dash of 0 is 0. Sometime in question paper they may ask question in another way as, so solve this equation with the help of Laplace transformation by, so this is this second derivative of y with respect to t plus y is equal to t. So this is the alternative method for asking the same question in the examination. So now friends, according to the method of solving linear differential equation by Laplace transformation, so apply Laplace transformation on both sides. So we get this as Laplace transformation of y double dash plus Laplace transformation of y is equal to Laplace transformation of t. So now this is because of the first step. Now we know that Laplace transformation of y double dash, Laplace transformation of y double dash is given according to this formula as, so we can write this as s square y bar of s minus s into y of 0 minus y dash of 0. So friends, this is the value of second derivative of y with respect to t. So now after writing this value, so next is plus Laplace transformation of y. Laplace transformation of y is denoted by y bar of s. So we can write this as y bar of s is equal to Laplace transformation of t. So we know that this is the standard formula. So Laplace transformation of t raised to n is equal to n factorial upon s raised to n plus 1. So friends, here value of n is 1. So we can write this as 1 upon s square. So because value of n is 1, 1 plus 1 is 2. So this is the first step, which is called as apply the Laplace transformation on both sides. Now second step is use the initial condition. So here initial conditions are y of 0 is 1 and y dash of 0 is 0. So put this value here, we get this as s square y bar of s minus s into y of 0. So y of 0 is 1, so we can directly write this as s minus y dash of 0. Y dash of 0 is 0, so we can write this term as 0 plus this is y bar of s is equal to 1 upon s square as it is. Now friends, rearrange this equation in such a way that we will find the value of y bar of s. So now collect the coefficient of y bar of s, so which is s square plus 1 into y bar of s is equal to, this is 1 upon s square. This is minus s. When we take to this side, this become plus s, right? So this become plus s. Now just simplify this equation. So we get this as s square. So then this is 1 plus s cube, or we may write this as s cube plus 1 upon s square. So now in this way we require the value of y bar. Now once again rearrange, we get the value of y bar of s is equal to, this is s cube plus 1 divided by, so this is s square into s square plus 1. So this is our step number 3. Now step number 4 is to apply the partial fraction concept, so that we get equation in the standard form and we can easily apply the concept of inverse Laplace transformation. So now friends, here observe that this s square is quadratic, this is also quadratic, so then there are two different methods for finding the partial fraction of this term. I will discuss this method here. So this is the first factor which is repeated twice. So this is repeated twice, so we can write this as a upon s plus b upon s square, because according to the repeated factor concept we write this step. Now this is the quadratic factor, we can write this as cs plus d divided by s square plus 1. So this is the one method to find the partial fraction. Alternative method is that this is quadratic, we can write this as as plus b upon s square plus this is cs plus d upon this is s square plus 1. So this is one way, this is second way, but in both the way you will get the same answer. So now here we will apply this method. So in this method also, if we apply this method, then also we will get the same answer. Now friends, try to apply this method. So according to this method, we write this as s cube plus 1 is equal to. So now write this as s cube plus 1 is equal to a into, so if we take this to the side, then we get this as a into s, then s square plus 1 plus this is b into, so this is s square plus 1 plus cs plus d into, we get this as s square. Now friends, to get the value of s, this term a, we may put the value, so it is not possible to get the value of a because s is present here, so this is also available here. So now to get the value of b, so put the value of s is equal to 0. After putting s is equal to 0, this term as well as this term becomes 0, we get the value of b. So now put s is equal to 0, so we get this as 1 is equal to, this is 0 plus this is b, so plus 0. So this straightforward implies that b is equal to 1. So this is the first value. For our simplicity, we write here b is equal to 1. Now once again simplify this equation so that we get the value of remaining term. So we can write this as s cube plus 1 is equal to a, this is s cube plus as plus bs square plus b plus c s cube plus d s square. So now arrange according to the decreasing power of s. So large coefficient of s is 3, so we can write this as a plus c, this is a plus c. Now coefficient of s square, so there is two terms, so there are two terms b and d. So next is coefficient of s, which is a only. Now we can write this as a plus constant, so there is only one constant term, so we can write this as only b. So this side is s cube plus 1. So now compare the coefficient. So 1 is equal to a plus c, so coefficient of s cube is 1, here a plus c. Now coefficient of s square is b plus d, so that means 0 is equal to b plus d. Then we get coefficient of s is a, that means we directly get the value of a as 0. Then again we get the value of 1 is equal to b. So from this equation we straightforward get the value of two constant a and b. Already we know the value of b is equal to 1, so here also we get the value of b is equal to 1, a is equal to 0. Now find the value of c and b. So from this first equation 1 is equal to a plus c, then put the value of a is equal to 0, we get the value of c is equal to 1. Then to get the value of d, so we get this as 0 is equal to b plus d. So now put the value of b is equal to 1, we get the value of d is equal to minus 1. So in this way, we get the value of all this term with the help of partial fraction. So I will write here value. So value of A is equal to 0, B is equal to 1, then C is equal to 1 and D is equal to minus 1. So this value we have obtained with the help of partial fraction. Now let's put this value in this equation. So after putting this value in this equation, we get next step as, so put this value here, so we get this as A 0, so we get this as 0 upon S, plus B is 1, this is 1 upon S square, plus C which is 1S minus 1 divided by S square plus 1. So this is the value after putting constant A, B and C. So now apply the inverse Laplace transformation to both sides. So after partial fraction, apply inverse Laplace transformation. So if we apply inverse Laplace transformation to this term, then we get this as inverse Laplace transformation of, so this first term is 0, so obviously answer is 0. So 1 upon S square, next term, plus if we apply the linearity property here, then we get this as S upon S square plus 1 minus, this is inverse Laplace transformation of 1 upon S square plus 1. So we write this according to the linearity property for the inverse Laplace transformation. Now friends, this is straightforward in our standard form. 1 upon S, so here also 1 upon S means Laplace transformation of t, so which is t. Now this is plus again standard form, this is cos of t, S upon S square plus A square, value of A is 1, that's why cos of t. Then this is minus, again this is the value of sine of t, where the value of A is 1. So this is the third example we discuss here. Now let's take the fourth and last example of this video lecture. So now fourth example. Now friends, let's solve the fourth example. So this is the last example of this video lecture. So solve this linear differential equation with the help of Laplace transformation. So second derivative of y with respect to t plus 4 times derivative of y with respect to t plus 8y is equal to 1, and initial conditions are y of 0 is 0 and y dash of 0 is 1. So now apply the first step, apply Laplace transformation to both sides. So we get this as Laplace transformation of d square y upon dt square plus 4 is constant, then Laplace transformation of dy by dt plus again 8 is constant, Laplace transformation of y is equal to Laplace transformation of 1. So Laplace transformation of 1. So now we know that, so this is the first step. So now we know that here second derivative of y, according to this formula we can write this term as, so s square y bar of s minus s y of 0 minus y dash of 0. So friends, this is the value of Laplace transformation of second derivative of y with respect to t. So plus 4, then Laplace transformation of y with respect to t, that means Laplace transformation of y dash, we can write this as s into y bar of s minus y of 0. So this is the first derivative of y with respect to t, then plus 8 into Laplace transformation of y, we can write this as y bar of s is equal to, so we know that Laplace transformation of 1 is 1 upon s, so we get this step as 1 upon s. So this is the first step. Now second step is use the initial condition. So here initial condition is y of 0 is 0 and y dash of 0 is 1. So we can write this as s square y bar of s minus, so y of 0 is 0, so this total term is 0, minus y dash of 0 is 1, so we get this as 1. So then this is 4, then this is s into y bar of s, then y of 0 is 0, so this term is again 0, so we write this as 0, plus 8 times y bar of s is equal to 1 upon s. Now friends, our next step is that, so find the value of y bar of s. If we collect all the coefficient of y bar of s together, then we get this as s square plus this is 4, so this is actually 4 into s, so we can write this as 4s plus 8 into y bar of s is equal to, this is 1 upon s. So we take this term and this term, so this 1 is remaining. So after taking this 1 to the right side, we get this as plus 1, we get this as s. So this is s plus 1. So in this way we get the value of y bar of s is equal to, this is s plus 1 upon s into s square plus 4s plus 8. So friends, in this way we get the value of third step, which is y bar of s. Now next step is to apply the concept of inverse Laplace transformation. But for applying the concept of inverse Laplace transformation, this equation is not in our standard form. So to get the standard form, apply the partial fraction. So these terms are non-repeated, so a upon s. So this is quadratic factor. We can write this as bs plus c divided by s square plus 4s plus 8. So now simplify, this is very simple example. S plus 1 is equal to a into s square plus 4s plus 8 plus this is bs plus c into s, after taking this denominator to the right side. So we get this as a s square plus 4as plus 8a. So take this a to the inner side. So multiply this to the s term, we get this as bs square plus cs. Now arrange this according to the decreasing power of s. We write this as a plus b. This is a, this is b. Now coefficient of s, which is 4a plus c plus 8a. Constant is only one term, which is 8a, and this side is s plus 1. So now compare the coefficient of like power term. So here s square term is absent. We can write this as 0 is equal to a plus b. Then we get this as 1 is equal to 4a plus c, and directly we get this as 1 is equal to 8a. So from this last equation, we directly get the value of a is equal to 1 upon 8. For our simplicity, I will write here, so which is 1 upon 8. Now from this first equation, if a is equal to 1 upon 8, then we get the value of b. So b is equal to minus 1 upon 8. So next value is b, which is minus 1 upon 8. Now find the value of c. So 1 is equal to 4a plus c. So we can write this as c is equal to 1 minus 4a, which is 1 minus 4 into 1 upon 8. So we get this as 1 upon 1 minus 2. So 2 is common. So we get this as 1 upon 2. So now value of c is 1 upon 2. So we write here c is equal to 1 upon 2. So in this way we get the value of all constant term together. So now put all this value in the given equation. So we get the partial fraction of this equation. So now after putting this value here, we get this as a is equal to 1 upon 8, 1 upon 8 upon s plus b. b is minus 1 upon 8s plus c, which is 1 by 2, this whole thing divided by s square plus 4s plus 8. This is s square plus 4s plus 8. So now here this is our standard form. Now we have to rearrange this equation so that we get the standard form and so on. So now take the inverse Laplace transformation on both sides. So if we take the inverse Laplace transformation on both sides, then we get next step as, let me first clear this board. So now here if we take the inverse Laplace transformation of y bar of s. So take the inverse Laplace transformation on both sides. So this is our step number 5, which is equal to, this is 1 upon 8 into inverse Laplace transformation of 1 upon s. Now according to the linearity property for the inverse Laplace transformation, we write this as minus 1 upon 8 into inverse Laplace transformation of, this is s upon this term, we can write this as s upon s square plus 4s plus 8. Then again this is plus 1 by 2 into inverse Laplace transformation of 1 upon, this is s square plus 4s plus 8. So now after applying the linearity property we get this step. Now friends, once again simplify this. So this is 1 upon 8, then inverse Laplace transformation of 1 upon s means this is 1 minus 1 upon 8. So this equation is not in our standard form. So let's first convert this equation in terms of standard form and then apply the result for the inverse Laplace transformation. So we can write this as inverse Laplace transformation of s upon. So if we observe the first two terms, this is s square plus 4s. So we get these two terms because of the term s plus 2, its square. So its square is s square plus 4s plus 4. So we get here as plus 4. Now here we get the value, we require the value of 8. Now we get here as plus 4. So again add one more 4 so that we will reach to this answer. So we will rearrange this as s plus 2 its square. So we write this as s plus 2 its square. Then again we write this as plus, this is 2 square which is 4. Now we write this as 1 upon 2. Again this is inverse Laplace transformation of 1 upon, this is s plus 2 its square, because first two terms are s square plus 4s. So this is the term. Now here also we required 8. So we can write this as plus 2 square. Now friends, it is always possible for us to find out the value of this term. So we can write this as 1 upon 8 as it is minus 1 upon 8. Now to apply the shifting theorem, so here 2 is added to the parameter s, but s is also present in the numerator, so that we can rearrange this equation in such a way that we can apply the concept of second shifting theorem for the inverse Laplace transformation. For applying the second shifting theorem for the inverse Laplace transformation, so we have to add plus 2 in numerator and subtract plus 2 from the numerator. So we rearrange this as inverse Laplace transformation of s plus 2, then minus 2 divided by, this is s plus 2 its square plus 2 square. Now this is plus 1 upon 2. Now straightforward, this equation is in the second shifting theorem for inverse Laplace transformation. We write this as e raised to minus 2t into inverse Laplace transformation of 1 upon s square plus 2 square. So straightforward second shifting theorem for the inverse Laplace transformation. Moreover, we can write this as 1 upon 8 minus 1 upon 8. So these are the two terms. So we can split this into two parts, or we may write this as e raised to, so this is e raised to minus 2t into inverse Laplace transformation of, we write this as s minus 2 upon, this is s square plus 2 square plus 1 upon 2 e raised to minus 2t. Then this is the standard formula for sine of 2t into 1 upon 2. So straightforward formula. So but this is the first term, this is the second term. So again split this into the two parts. So we get this as 1 upon 8 minus 1 upon 8 e raised to minus 2t. So then this is inverse Laplace transformation of s upon s square plus 2 square first term minus 2 times inverse Laplace transformation of 1 upon, this is s square plus 2 square plus 1 upon 2 e raised to minus 2t. So this become 1 upon 4 into sine of 2t as it is. So now just find out the inverse Laplace transformation of this 2 term. So we get this as 1 upon 8 minus 1 upon 8 into e raised to minus 2t. So now friends, this is the standard result of cos of 2t minus 2 time. So this is the standard result of sine term. So we get this as 1 upon 2 into sine of 2t plus 1 upon 4 e raised to minus 2t into sine of 2t. So friends, in this way we will get the answer to this term, or you may combine this sine term together and we get the different answer after combining these two sine term. So here friends, we solve 4 example based on the applications of Laplace transformation for solving the linear equation. So now for your practice purpose, I am providing some examples to you. Friends, in this video lecture we cover the examples which are related to the analytical part for applying the concept of Laplace transformation to the linear equation. So in our next video lecture, so we are applying the concept of this Laplace transformation for solving the electrical engineering related problems. So our next lecture is based on solving the electrical engineering related problem based on the linear equation by Laplace transformation. Now let's take some examples for your practice purpose. Now friends, time is to test your knowledge. So now here for your practice purpose, 7 examples are given. So first example is 3 times derivative of y with respect to t plus 2y is equal to e raised to 3t. So y is equal to when t is equal to 0. So this means that y of 0 is equal to 1. So that is the meaning. So in another way they represent this equation. So this is the answer related to the first question. So now here to solve this equation, derivative of y with respect to t plus 3y is equal to 2. So if we take the Laplace transformation of this function, then we get this as 2 into Laplace transformation of 1. So that we can find out the Laplace transformation, and this is the answer which is related to the second question. Now this is the third question. So in this question we represent capital D. So where capital D stand for, so this D stand for derivative, so dy stand for derivative of y with respect to t. That means D stand for d by dt. So we know that with the help of linear differential equation, this notation. So this is the third. Now this is the fourth equation, so which is simple one. Initial condition is y of 0 is 4 and y dash of 0 is minus 2. So this is the answer. So now this is the fifth question, which is very straightforward. Now sixth question, so this side is 9. Again 9 means we can take this as 9 into Laplace transformation of 1. So here x is equal to 0, y is equal to 0, dy by dt is equal to 0. So that means y dash of 0 is equal to 0. So that is the meaning of this condition. So now this is the answer. Now last question again. So d stand for derivative with respect to t. So this d notation is for derivative with respect to t. So now friends, here solve this example. So this is the answer which is related to this question. So solve all these 7 questions independently. Verify your answer with the answers given on this board. So friends, we stop here. So this is our first part of the applications of Laplace transformation to linear equation, where we solve the applications which are related to the analytical part. In our next video lecture, we are solving the example based on the applications, engineering applications related to the Laplace transformation. So please watch our next video lecture, applications, engineering applications we are solving with the help of Laplace transformation. So friends, I hope you like this lecture. So thanks one and all. Thank you.